As we have learned, there is another memory pool in the JVM called the code cache, which is used for storing the compiled code generated by the JIT compilers. This memory space can also get filled up, and we can come across the warning message saying that the code cache is full and the compiler has been disabled. Let's see what this warning message means and how we can resolve it. As I said, the code cache is the memory pool which is used to store the generated compiled code. There's no out of memory error thrown when the code cache becomes full, but a warning message is printed by the JVM indicating that the compiler has been disabled and it won't be generating any more compiled code. The compiler stays disabled until there is some room available in the code cache. The code cache is not managed by the garbage collector. It has its own separate collector called the sweeper. Now when the code cache becomes full, an emergency code cache cleanup is invoked. But the disadvantage of this emergency cleanup is that it may discard the compiled code that may be needed shortly after. And then the JIT compiler has to work again to generate the compiled code for those methods. This can have a negative impact on the application performance. To avoid these performance penalties, we should make sure that the code cache is sized appropriately. The JVM option to configure the maximum size of the code cache is reserved code cache size. These error messages clearly tell us that the JVM is not able to allocate from native memory, which could be due to the fact that the JVM process itself is consuming all of the available native memory, or there are other processes on the system that are eating up the native memory. Let's take a look in detail at the out-of-memory error exceptions for native memory. These two examples show that the JVM process has run out of native memory. We encounter native out-of-memory errors when the JVM is not able to allocate from native memory, which is not directly managed by the JVM. This can happen when the current process or other processes are using all of the available native memory. We can try to make more room for native allocations by reducing the sizes of Java heap, metaspace, reducing the number of threads, their stack traces, and by terminating some of the processes that we don't need running on the system. If all of these measures don't help and we still run out of native memory, then we should investigate if there is a native memory leak. For example, we might have JNI code that's allocating buffers in native memory but is not deallocating them appropriately. Let's take a look at some of the common native out-of-memory issues. As we know, running with a 32-bit JVM puts a maximum limit of 4 GB on the process size. So you are more likely to run out of native memory when using a 32-bit Java process. However, when running with a 64-bit JVM, we get access to unlimited address space. And technically, we would expect never to run out of native heap with a 64-bit JVM. But in fact, that's not the case, and it's not uncommon to observe native heap out-of-memory errors occurring in a 64-bit JVM. This is due to the fact that the 64-bit JVM by default has a feature called compressed OOPS enabled by default. And the implementation of this feature determines where the Java heap should be placed in the address space. The position of the Java heap can put a cap on the maximum size of the native heap, and that can lead to native heap out-of-memory errors. This memory map shows that the Java heap is allocated at the 8 GB address boundary, leaving around 4 GB space for the native heap. Now, if this application allocates intensively out of the native memory and requires more than 4 GB, then it would throw native heap out-of-memory error, even though there is plenty of memory available on the system. This problem can be resolved with the JVM option heap base min address. By using this option to base the heap at a higher address, we can leave more room for the native heap to grow. Let's see how inappropriate use of JAXB can introduce out-of-memory errors. JAXB internally uses inflator-deflator classes to compress and uncompress files. Inflator and deflator internally use native memory to hold their data. and these depend upon finalization to collect the used native resources. Now, if for any reason finalizer thread cannot keep up and does not deallocate native memory fast enough, then the process is at risk of running out of native heap. So it's important to keep a tab on the pending finalization queue and monitor the number of inflator-deflator instances building up in that queue. Another common JAXB related issue occurs due to a mistake in the usage of new instance method of JAXB context. If in the code new instance is called for every new request for a specific context, then the classes from that context get reloaded every time. It wastes the meta space and also increases the native memory usage. One more issue which we have seen pretty often arises from environment upgrades. If a system environment upgrade that upgrades the JDK and other components of the system but somehow fails to upgrade all the JAXB files or leaves behind old versions of some of the JAXB jar files could result in class linking errors at the runtime, leading to reloading of the JAXB classes. That in turn wastes meta space and native memory. Now let's see how the use of direct buffers can cause out-of-memory errors. Using allocate direct of byte buffer, we can allocate directly into the native heap. It creates a Java object direct byte buffer and the underlying byte array is allocated in the native heap. When a direct buffer is created, the JVM attaches a phantom reference to the direct byte buffer Java object. When that Java object becomes phantom reachable, it gets collected at the next garbage collection cycle. And a new entry is added to the associated reference queue. A separate thread called the cleaner thread is responsible to go through the entries of this reference queue. And when it reaches this added entry, it runs its registered cleanup action, and that action deallocates the associated native memory. Applications making intensive use of direct buffers may exhaust the native heap. So we have to be careful while using direct buffers in our applications. The maximum direct memory is unlimited by default, but it can be limited with the JVM option max direct memory size. The Java NIO APIs use byte buffers as the source and destination of native IO calls. These APIs use Java heap byte buffers and direct native memory byte buffers. Heap byte buffers allocate a byte array in the Java heap. Direct byte buffers allocate memory outside the Java heap using malloc. System or native IO calls can only use native memory, as native memory allocations cannot be moved by the garbage collector. This means that when we use a Java heap byte buffer for IO, it is copied into a temporary direct buffer. The JDK caches one temporary buffer per thread without any memory limits. As a result, if we call IO methods with large heap byte buffers from multiple threads, our process can use a huge amount of additional native memory, and which can look like a native memory leak. In JDK 9, a new property max cached buffer size has been added that can be used to limit the size of these temporary direct byte buffers. Let's look at the diagnostic data that can help us troubleshoot native memory leaks. Native memory leaks can be in the native allocations performed by the JVM or in the native allocations outside the JVM. For the memory leaks in the JVM, the diagnostic data that we should collect is the output from the native memory tracker or the NMT tool. For diagnosing outside JVM memory leaks, we can use process maps from tools like PMAP and results and analysis from the native memory leak detection tools such as libumem and valgrind. Analyzing different segments of the code file can also provide useful insights into the usage of native memory. The JVM has a powerful feature called native memory tracking that can be used to track native memory used internally by the JVM. Please note that it cannot track memory allocated outside the JVM or memory allocated by native libraries. To use NMT, we need to start the Java process with the JVM option Native Memory Tracking that enables the memory tracker. This option can be used at summary or detail level that sets the verbosity of information we would like to see. After the JVM process is launched with NMT enabled, we can use the JCMD tool with command vm.native_memory to connect to the process and retrieve native memory usage information. We can do this at different stages of the process and compare the native output to understand where the internal JVM memory usage is growing. With NMT, it is also possible to collect a baseline first and compare the subsequent snapshots of information against that baseline. This example shows the output from the Native Memory Tracker tool. This output provides information about the internal memory usage by different components of the JVM, such as the Java heap, threads, code, GC, compiler, and symbols, etc. Comparing the NMT output collected at different stages of the runtime with the baseline can get us valuable insights as to whether there is any unexpected memory growth for any area of the JVM. For the native memory leaks stemming from outside the JVM, we need to rely on the native platform's memory leak tools for their detection and troubleshooting. Native tools such as DBX, libumem, valgrind, purify, etc. can rescue us in dealing with the outside JVM native memory leaks. For more information on how to troubleshoot various issues that might occur with our Java applications, please refer to the Java troubleshooting guides. The links to the JDK 8 and 9 troubleshooting guides are shown here. To summarize what we have learned in this lesson, there are several kinds of out-of-memory errors with different messages. It's important to clearly understand what these messages mean so as to know which memory pool we should be focusing on while troubleshooting a particular out-of-memory error exception. And here's the list of tools that we can use to troubleshoot memory problems in Java applications. And that brings us to the end of the lecture videos for lesson 3. You are ready to try lab 3 now, where you'll first run a Java program that shows memory usage growth in the Java heap space. You'll create a heap dump from the Java process and then analyze that heap dump with the Eclipse Memory Analyzer tool to find the root cause of memory growth in the Java heap space. Then you'll run another lab program with JDK 8 or 9 that shows memory usage growth in the meta space. In this case too, you'll be creating a heap dump and will analyze that heap dump with the Eclipse Mat tool to figure out what's causing the meta space to get exhausted and how we can resolve that. This was the last lesson of the course. Hope you have enjoyed it. Thank you.